Alright. Hi everyone, I'm Mel, and I'm going to be talking about some of the work that my wonderful team, our wonderful team, did on the Environment Agency's challenge of making decisions using uncertain forecasts. So I'm just going to sort of recap the problem and where we started with. Then Michael's going to take over and go talk about where we went with it, and Jonathan's going to tell you about where we ended up. So just to recap the rationale for why we want to be doing this kind of thing. So probabilistic flood forecasting, it can provide a range of benefits when compared to conventional deterministic methods. Basically, it's a technique for incorporating ideas around the kind of inherent uncertainties associated with forecasts, particularly in a flooding context. And it allows action to be taken earlier if you have a better sense of what your forecasts are actually telling you. However, more information does not necessarily result in better decision making, and we'll sort of give one example of that a bit later. And so for us, the challenge is how do we take forecasts, so particular scenarios that could happen, particular actions that we could take, and make a decision about which one's the best decision to make. And this, in the context of the Environment Agency, this is going to have to be applied to different kinds of decisions, so routine decisions around issuing flood warnings, closing flood barriers, but also some sort of reactive rule of thumb kind of decisions. And so we were really trying to, with the things that we developed, make it so that both of these decisions can be incorporated within it. So just to provide a bit of a concrete example for as we go through, we're going to look at the Colne barrier, and this is basically a particular flood risk management technique of if you've got a high prediction for water level, you can decide to raise the barrier or not. And I'm sorry about the small font, but I'll talk you through it. So one thing to point out here, you've got a low decision cost. So the cost of the raising the banner is relatively low, it's £4,000. And your potential return, if there is a flood that you avoid, you mitigate damage on the order about £2.25 million.
Where are you going to estimate the interest of the cost?
Yeah, so I'll actually talk a little bit about what that number means. But for broad predictions, another thing to point out here is you've got, in this case, you're raising the barrier when there wasn't an event. So then you've got the associated cost here of that false alarm. And so that's just sort of providing context for needing a better decision. And the other thing to point out is here we're talking about ensembles. For anyone who's not familiar with that, an ensemble is essentially equivalent to scenarios, where we've been talking about it before. It's not quite the same, but it's just for a model you sort of have either various models or models running with different parameters will give you a different prediction of what's going to happen, and then you'll want to make a decision based on the outcome of these various ensembles, what their predictions are. Okay, so this was the case of raise barrier, don't raise barrier, and then sort of the flood goes over the threshold, the flood doesn't go over the threshold. Our problem was incorporating multiple actions you could take and multiple options. And we also wanted to look at this idea of the branching wait and see decision. So that's kind of four things. You've got the kind of single option, single action, multiple option, multiple action, and assessing the impact of delaying your decision. And so our objective was to develop an easy-to-use decision-making tool that can be applied in those four cases. And then just as a sense of where we started from, this was the model that we wanted to play around with a bit, but obviously where we got to was one where you could specify different actions to take and different prediction or ensembles inputs. And these are just some sort of rough numbers that we put in, but to give a sense of you have some high cost options with a high damage reduction in the worst case, and some lower cost with a less the damage reduction. And the costings that we were working with, just to sort of help people follow through, these were the costings for raising the barrier, and then when we started to incorporate different actions, we just sort of took a breakdown of what was informing this costing decision, and sort of made some educated guesses on what impacts the different actions would have on the potential damage. So evacuating would reduce social damage, risk to life, but probably isn't going to do anything to your property damage, etc. And so I'm just going to hand over to Michael now. He's going to talk through the rest of it. Oh, we need this.
Okay, can everyone hear me okay?
Yeah.
Brilliant. So this is sort of, right clicker, this is sort of the classic problem of where you've got multiple actions you could consider. So this is like the raising your barrier, this could be your evacuation scheme and so forth. You've got your different states or scenarios, so these could be your different ensembles, and then you've got what those ensembles are telling you will happen if you take that action. So these are your payoffs. Now what we can currently do, and these methods have been around for a significant length of time, is to basically evaluate this grid and tell you what the optimum course of action is. So you could base it on sort of your average payoffs, your minimum payoffs, your maximum, your regret, or some sort of weighting between the two. Now what we do in flood incident management currently is the average, and I'm going to talk why this might be a problem. And the other issue is that you can evaluate these grids both as static problems, so this would be sort of designing a seawall, but you can also apply them as sort of a series of little decisions, so in this example gradually building up a seawall over time, and you can evaluate the costs in both functions. So this is actually the title that we were posed by Adam, and I'm going to be a little bit cheeky, that I want to cross out the word probabilistic, and I'm going to explain why now. For me, the issue is not the information in this grid, it's the information that we are deriving from the ensembles, our probabilities. This is a standard ensemble run. This is basically the deterministic portion, and this is what could happen. Generally speaking, there is a probability distribution here. It could be uniform. These could be equally likely. And this is another ensemble run. So this is depth. This is the different model realization. So you've got some which are going to be very extreme. You're going to have lots of damage. You've got some sort of low. Now the way that we currently estimate the probability, this is the probability of this event happening, is in essence the frequency, probably the easiest way to show it this way. If these are our different ensemble members, this is the maximum depth that it recorded. We compare that to the threshold that we can protect to, and we say whether it exceeded the threshold. So whatever it was, 3.3, so this is higher than that, so there's going to be a damage, it's going to exceed the threshold, and apparently the probability of this happening is 38%. Now, bearing in mind, this is the probability of an ensemble distribution. An ensemble can be produced from varying the parameters within a model, varying the starting conditions within a model, give you an idea of sort of the parameter uncertainties. You can also do clever things like multi-model ensembles, in which case you consider the sort of structural uncertainties. But this probability is not the same as the probability in reality. They are drawn from two different distributions. Sort of the classic analogy is all models are wrong, some are useful. The one I prefer to say is that a model is a simplification of reality designed for a specific purpose. So there's a number of caveats within that. One is we won't know this number for certain. It might not be credible. And second, actually, if we start messing around with sort of things like this on the decision end, we can misinterpret the way the forecast was originally sort of produced. And just to, this is just some summary points. I thought I would include Wikipedia if people want to sort of, I can only talk broadly around this subject. I do encourage you to read more. This is sort of the current standard advice by the World Meteorological Organization in terms of what it means by probabilities. And without going too much into the detail, it is broadly summarizing that probabilities within the ensemble are not the same as reality, and we need to interpret them with care. Which brings me on to the data and why this then becomes an issue. So, ignoring the issue of probability and whether that decides we take an action, we then have to look at how they estimate the costs and then how those costs lead us to take an action. So, this is probably a classic example where they're estimating the current damage as the average of this row, okay? And because this cost is higher than the basically the action, £4 grand to raise the barrier, they take the action. Now, if you look at this data, what you will see is actually there are a large proportion of ensembles where you haven't actually reached your threshold, yet you are taking the action. And that's simply because the action decision is based on the average of these. So we wanted to come up with a sort of a more clever way of trying to interpret the information within ensembles, recognizing that we don't necessarily want to use probabilities, but each one of these ensemble members has potentially useful information, and we don't just want to average what we think is going to be the expected outcome and then use that to inform the decision. As you can see here, we've included the false alarm. So this is basically where this is what actually happened, the observed. These are your ensembles, and the ensembles are producing false alarms, which is basically they're saying you need to take an action, and then the observed is saying not. So that's because there's a difference in terms of model and reality, but it's also a byproduct of this sort of economic element. So based on that assumption, this is just one option. You could extend this in sort of a multiple dimension. So you've got your ensemble runs. Now you've got multiple options. Now the interesting thing about this data is that the average of each of these lines is equal. So if we were to interpret as we currently do on the average, you would not be able to distinguish between these sets of options. However, if you look at the payoffs, for example, the worst case in A, worst case in B, there is a different outcome. I've ranked these just to make it a bit easier, but generally speaking, if we do the average, we ignore the usefulness in this information. So as a result, oh yeah, you can do other things like look at the worst case. This is just references. You can do something else. So we worked on sort of programming this criterion, which is a more user-defined decision support tool, I guess you can call it, which is basically a way of interpreting this grid based on your individual priorities. And they could be conditioned based on sort of prior knowledge or sort of ongoing challenges and actually what you want to focus on. So, as I said, I did this example yesterday, but just to remind everyone, is if you were to look at these three options, the average of these three options, so A basically is always increasing, B does this, and then C does this, the average of those three lines are equal. But if I was to ask in this room, do you have a preference? Some people are going to tell me it's option A, because they want to get the big wins. Some are going to say B, and some are going to say C. So there is a sort of a risk-adverse, risk-seeking perception that we need to capture within our evaluation. So this is the equation that I showed you yesterday. I'm not going to expect you to try to understand it now. I'm going to give you a tutorial. So this is the hypothetical three-problem decision. What you do is you calculate your maximum and your minimum bounds based on the outcomes of those. You specify, in essence, a band. So the idea here is that you can define how far this band extends across the data. So you could look at the full data and you could basically say, where is each option relative to that band? So you might have a situation where you make this very narrow and you prefer the option which is always at the top, as opposed to an option which might do something like loads of negatives but a massive payoff because they would give you the same outcome. You then specify a threshold, so this is just to avoid the criterion avoiding selecting against negative outcomes, so you can again define that based on prior knowledge, and then it's just a weighting coefficient to determine whether you're more concerned about the sort of positive outcomes, the negative outcomes, and then make an informed decision. And then you score. So let's try this because I want to have a quick go. So in this room you've got three options, A, B and C. Who thinks the red line is the best option? Just a show of hands of the three options.
We're looking at the EA, right?
Well, no, just as a broad show of hands. So, and you've only got one vote. So who prefers option A? I did say they all have equal lines, but okay, one, couple, few. Okay, who prefers option B? Okay, and option C. Ah, okay. So we've got a slightly different result, but this will prove a concept. So I've arbitrarily set these coefficients because I tried to guess what the people were in this room. I didn't guess very well, but I got close. So this is just some arbitrary assumptions that, again, we would probably generate through prior knowledge. This is the implementation, and that's what we scored. I thought, guessing in this room, that option B would come out as the best option based on those thresholds. But you can see you can quickly tailor any of those parameters, and it will allow you to basically rank your different options based on what are your priorities. And the advantage here is obviously when we start thinking of the process of flood warning, you've got your lead time, you've got your actions. You can start to evaluate that using sort of decision trees. So you can look at the accumulated cost. You could also do things like look at the model credibility here, and then a day when you've improved the confidence intervals, you will obviously regenerate your ensemble. And I'm going to just pass across. Oh, yeah.
Great. Okay, so that's some of the ideas that fed into the tool we were going to use, and deals with the idea of the multiple option, multiple action. And now I'm just going to summarize some of the ideas we had around what to advise about when it comes to delaying a day. So what's the benefit of delaying a day? Well, basically it means your prediction is going to be your current prediction will be more accurate when you're closer to the day. So this top one is just some simulated data on river flows, and one day out you can see the red line there is the observed, and the purple line is the predicted, and these are much closer when you're one day out to when you are 3 days out. It's fairly straightforward. But so when it comes to looking at what that means for when you're a day out, you're basically trying to assess what's the cost of making the wrong decision because of your uncertainty. And so that sort of splits into two questions. It's how does your credibility change as you get closer to the event, and what impact is that going to have on your likelihood of making a bad decision, and what's the cost of that bad decision. And so option one that you definitely can do is to use historical data, and you calculate the expected cost of bad decisions. And that's fine. It does rely on having the data, and it also, with the kind of tool that we're developing, is potentially quite costly to go through, because what you want to do is to simulate what decisions you would make in that context for varying options and varying predictions, etc., etc. And so another thing that we were sort of trying to thrash out was this idea of using a relative reliability score, and that's sort of estimating this idea of how it changes, how your credibility changes as you get closer. One of the ideas that we were sort of playing around with was the analogy of a hurricane. So when a hurricane strikes, it sort of spreads out, and you could sort of look at your error bars around your prediction as that kind of idea. It spreads out, and in different times or locations, it's going to hit in different places, but the spread might be roughly the same, and you want to sort of compare the cross section. And so what in this case, we're taking this kind of window on your current error. And this isn't the same as saying what decision you would make tomorrow, because you don't have any information about what your prediction is going to be tomorrow, but you do have information about what your credibility is going to be like. So it's basically just comparing where you sort of go to either two ends of the potential error bars, that you can think about it like that, and you sit at the maximum minimum of your outer error bars, in a sense, and you kind of go, would you make a different decision? And then you sit at the inner area and you say, would you make a different decision if you had more confidence? And there's a lot of things that aren't quite worked out in that, and a lot of things that can change. But it gives you a good sense of, are you in an area that is particularly sensitive to the uncertainty, and is your decision particularly sensitive to your uncertainty, which could be used to inform whether or not you delay your decision. And so now jumping to the chat through where we actually got to.
5 more minutes.
Yep.
So, ultimately our goal was to implement this procedure that would make the decision in code and then demonstrate its effectiveness. In order to be able to run it, though, we need to come up with the decision matrix as was described earlier. This is the matrix where the columns of it refer to the different ensembles, the different things that might happen, and the rows apply to the different actions that we might take. This is how we constructed this matrix, where we considered our various actions. Each action would have a cost of running this action. So building a seawall has a cost, evacuating everyone has a cost. Each of these actions would avoid a certain amount of damage if a flood was to occur. We needed to take, we We needed to know the expected amount of damage that a flood would cause if it happened, and we needed to know how much of a flood we might expect to happen. By putting all these three things together, we constructed the decision matrix using effectively this formula right there, where the function f is something that we would have used linear interpolation based on the data we were provided with. Now, in order to test this, what we did is we generated random ensembles. Why did we generate random ensembles? In practice, when you have your predictions of what might happen, these predictions typically are fairly close together. If that's the case, our procedure would typically say, here is a good answer. We wanted to rather show our tool and how it would work and why the tool is interesting. So, in this case, what we did is we generated 24 random data points where they could range in values between 2 and 5, which were in practice the data we'd get from the ensembles in terms of what the depths of the rivers would be. When we put this into the matrix, we would, for a particular value of b, which was our robustness coefficient, I'll remind you in a moment of what this was, this is we got in terms of what our optimal course of action would be. Now, to remind you what the robustness coefficient was, when Michael was discussing that green strip of space along your option area, b was how thick that strip was. So the smaller b is, the more you are really determined to have a solution that is good as often as possible, and the bigger b is, the more you're taking into account all things that can happen.
Other way around.
Oh, really? Apologies.
So yeah, the best way to think about it is one is 100% of the data, top 20% of the data. So it's basically saying as you use more or as you reduce the band, your options, so start again. When you use the average, which is sort of what we currently do, so the full data set, you would always do the barrier. But as you focus your assessment onto the best performing options in that sort of narrowing band, actually the options priority set changes. So actually by sort of interpolating across the ensemble, we can get an idea of actually how the robustness of different options changes. In essence, this is an artifact of having a very extreme event in the ensemble. So if you look at the average and have all the data, you're always going to do that. But actually, if you start looking at sort of the relative positioning of each of your options within your range, actually, something like evacuation is sort of near the top and it gradually improves. So actually, it's a nice way of trying to prioritize different actions based on how confident you are and what you think the robustness is.
So ultimately we get is, depending on what our priorities are, the choice that we might make will change.
I think that's an extra slide. I think we've somehow...
Okay, so what have we come up with at the end of the day? We have come up with the following outputs, where we have both a spreadsheet and a piece of Python code which will implement this algorithm. What they both require is a decision matrix be inputted, where it's of the form where the columns of this decision matrix are the different events that could happen, and the rows are the different actions that can be taken. In addition, what we require is the values of alpha, beta, and t, where alpha is how optimistic you are, between 0 and 1. Beta is the robustness coefficient, again, between 0 and 1. And t refers to that horizontal line, which, that, as illustrated earlier, which the bigger t is, the more desperate you are to have a good answer all the time. And what we get afterwards is we output the robustness scores of all the options that we input, that are provided, and in addition, which option has the best score, and therefore which one you should take given these input parameters. In terms of further things that could be done with this, if we'd like to, as things stood, we ran this with a combination of real data and generated data so that we could see that it was working and show what it was capable of. If we were to able to run it with real life data more consistently, that would be a further thing to show what this, the use of this. Also, we'd like to see what this would, what would have happened if we had used this kind of policy to make decisions based on historical data, because that would be a good indication in terms of whether we would regret using it or not. So we'd like to be able to test this with historical data to figure out which set of parameters, alpha, beta, and t, would be useful. And finally, at the moment, this takes into account options that are available right now. It doesn't, there isn't yet a way to work into how the other level of uncertainty, so uncertainty for tomorrow and the next day, and how that would fit into making a decision now, where you can carry out options now or tomorrow or the next day. So that would be another way that this method could be extended. And sorry, there used to be a question slide. So, and
there was some
Yeah.
uncertainty with the presentation, and just as there's probably no point showing the code because I'm sure John won't want to show that. This is basically your decision grid, your evaluation. That's your grid. These are your user-defined parameters. Watch what happens to the mean payoff. Doesn't change because that's the issue with the current procedure. But our utility, our ranking of options will change based on the data.
All right. Thank you very much. Other questions?
Working now? There we go. Thanks very much, guys. That looks great. I think that a simple spreadsheet is the sort of thing which would work wonders actually for incident management. People can input that kind of data fairly easily. One thing I think I need to speak to you about afterwards is the alpha, beta, and T, because if people see that on the spreadsheet, they'll do that. But I think we could probably get some presets for typical sorts of decisions that you could probably pick from a drop-down list. So yeah, I think that could work well. Well done.
Very good. Yeah. What? Right. Well, you have to go to the front shortly anyway, right? So, there you go.
Hi, this is really, really awesome work. You showed some data with a failed decision, a false alarm earlier on in the talk. I would be curious as to how this method works and see if you can get a better estimate of a decision you would take in that position, because obviously they've evacuated there and made a terrible decision, terrible mistake. But obviously, I would be curious as to know how your method works.
Yeah. So I think there's a couple of things we first want to do to sort of prove this. The one thing I'm very skeptical, although this was sort of provided to us, is this avoided cost function, because it's very difficult to sort of optimize the decision. On the point about whether we think we would avoid this situation, in principle, yes, because this is based on the average. So it's sort of that situation where you've got most of your ensembles are saying it's not going to flood, and then you've got one furious ensemble that's saying it's going to be sort of a tsunami. Whereas we're really evaluating across that set. So in theory, provided these are sort of reasonable, we should come up with a better conclusion.
It basically depends on what parameters you put.
Yeah.
So if you put it to be, we absolutely don't want to have any risk in any possible chance, even for the really spurious results, then this would be the exact same result. But that's, I guess, the point of using historical data to fine-tune your parameters.
Yeah.
When testing the code, one thing that we found is that if we weren't careful with the selection of parameters, we would keep on finding cases where it advised us to do nothing.
Yeah.
Okay.
Yeah.
So obviously the EA has got its own set of priorities and would need to inform that.
Yeah. And just sort of an amendment to that is, the issue we had was sort of the closing the floodgate. You had all of the benefits, the sort of benefits from social, etc. Now the other thing I'd like to sort of close on is, in essence, what we are trying to do here is shift the focus away from the ensemble, away from the probabilities, actually onto sort of the decision makers at the end of the process. So actually a lot more weight is given to their knowledge and their expertise, and not just trying to sort of creatively interpret the ensembles. And that's where we think the real value is.
Any more questions? No, let's join me in thanking